Adam will give us a talk on quantum error correction in SYK and the emergence of the model.
Okay. This is, I can't write on, I need to write on these 2 points, right? Yeah. This is going to be based on a paper that came out a little while ago that I wrote with Ben. So there are sort of these 2, well, I think historically sort of the first idea, one of the first ideas of how the bulk emerges in ADS CFT is related to our G flow of the boundary theory. And then sort of in the last, I would say like 10 years or so, there have been some maybe refinements, not necessarily different ideas, but sort of refinements, I would say, of how the bulk emerges. And 2 of the ideas that I wanted to focus on today, one of them is this idea of quantum error correction, which I'll remind everybody because not everyone here is probably an expert. And then there's also this idea of operator size, that when you perturb the boundary theory with some operator, the operator grows under time evolution in some sense. And I always felt that these 2 should be connected in some way. So what I'm going to try and do is argue for a bound that sort of relates the reconstruction of an operator using quantum error correction to its operator size. Okay, but to do that, let me review quantum error correction. So just so everyone's on the same page. So the way I'm going to think about it is that there's some isometry which embeds some small logical Hilbert space. So we have some Hilbert space. In this talk, it'll often be the Hilbert space of a single qubit, so a single logical qubit. And we want to encode it or embed it into a physical Hilbert space. This could be a Hilbert space of many qubits. In SYK, it's isomorphic to a Hilbert space of many qubits. So yeah, in this talk, I'm gonna think of my code subspace as being 2-dimensional, and my physical Hilbert space will have dimension 2 to the n. So it'll be a n qubit system. And this is basically all quantum error correcting code is up to. There are some errors that you want to be able to reconstruct or correct from. So the idea is that you have a qubit, you embed it into many qubits, and then you could lose some of those qubits, but the information of the original logical qubit is still there. So I'm going to say that this code subspace is reconstructible on some subsystem. This subsystem is a subsystem of the physical Hilbert space. If for all operators acting on the logical Hilbert space, O code, there exists an operator purely supported on this subsystem, which effectively commutes with the embedding map when acting on the code subspace. So that means given some logical operator, let's say this is 2-dimensional, so it's a qubit. This could be a sigma x. So this acts by doing a bit flip. Then you embed it into Hilbert space, and that means that there's an operator purely supported on A, which does that guy's job. Okay, on the code subspace. It might differ it might do some wild stuff outside of the code subspace, but we just care about what it does in the code subspace. So a big advance was that ADS CFT sort of naturally geometrizes this situation. So here I'm going to draw a time slice of ADS, say ADS3. So this is totally general. And you have some operator, let's say phi, which is supported somewhere in the bulk. I'm going to forget about dressing and all that stuff. Just let's imagine free field theory in the bulk and have some operator, and I want to reconstruct its action. I could consider a code subspace, which is what we'll do today, which is the span of 2 states. The span of the vacuum and the state with phi acting on the vacuum. Okay. Let's imagine that phi acting on the vacuum is orthogonal to the vacuum. And then what we know from the Ryutaki-Nagi formula is that given some boundary region, the prescription to find out if you can reconstruct this operator on that boundary region is to start drawing minimal surfaces. So this is some boundary region A, and if the operator that you want to reconstruct acts within the entanglement wedge of that boundary region, then you can, there's a map that maps phi to just an operator supported only on A. Okay. Good. So there's this nice paper a long time ago by Postowski and Preskill, where they introduced this notion called the price, which is sort of, you can see that in this situation, there was some extra room I had. I didn't need all of the Hilbert, all of the, let's say, I think of this boundary region as being some qubits. There was some extra space. I could have chosen a smaller region and had phi still be in the entanglement wedge of that region. So it motivates something called the price of a code, which is the min over all boundary regions of the size of that boundary region, such that H code is reconstructible on A. Okay. Now there's a notion of a measure of the boundary region here, and in different situations it might be different. So in higher dimensions, maybe you want to take some physical size of the boundary region. And what we're going to talk about today, this measure is going to be the number of qubits that you need in the physical Hilbert space to reconstruct this operator. Okay, so it's a cost of qubits. They also had something, so you can imagine a situation in ADS-CFT where your code subspace, let's say, is associated to a blob of qubits somewhere in the bulk. Maybe you have many qubits sitting around, or many degrees of freedom sitting around in some region in the bulk, maybe like someone like a black hole. And the price is related to the minimal region that can reconstruct this. They also introduced something called the distance, which is it's the minimal region such that errors on the code subspace are not detectable. Operators on the code subspace are not detectable from that region. Sorry, are detectable from that region, are detectable. So it's the minimal thing such that if I act with some operator, so let's say if I took some slice through this region, I could act with operators here, and they will be detectable from this boundary region, but I can't reconstruct the whole code subspace on this boundary region.
So it's the minimal region where you can detect some information.
Some information, but not all of the information about the code subspace.
What was that called again?
This is called, yeah. So this one is called the distance. So this is the distance surface, and this is the price. So it's pretty clear from the ADS-CFT picture that the distance of some code is always less than or equal to this. Okay, you won't actually need the distance, but I just thought I'd introduce it. And you can see that in ADS-CFT, if we shrink this down to an operator localized at a point, like in that situation. So if our code subspace is really just the span of these two states, then the distance and the price are equal, basically. Okay, that's a special property of these holographic codes. So Ben and I introduced the price motivated by this. We'd introduce the price of a boundary operator. Okay. So consider an operator which acts on your physical Hilbert space. Some operator, it's supported everywhere potentially. And you have some reference state, which I'm going to suggestively call beta, which in our case will be the thermal field double state, but in general, it could be something general. And if you have the condition that this physical Hilbert space, when it acts on beta, is orthogonal to beta, so in other words, it has 0 expectation value in this state, then I can consider a situation where I have 1 qubit's worth of information. I have the 0 state, and I have O phys acting on beta, which I'm going to call the 1 state. Okay. And so I can associate to this a code subspace of my physical Hilbert space, which I'm going to call H code of O and beta, which is just the span of these 2 states. Okay. And then I want to associate to this operator a price, which is just the price. So I'm going to call P beta of O is just the price of this Hilbert space, code subspace. Okay, so it's really just how many qubits do I need to detect the action of this operator on the thermofield double. That's it. Okay. And sort of what motivated this project was that, well, we had wanted to know in some sense, is this related to size? Intuitively, it feels like it should be. So now I know I need to explain to you what size is. But the question was whether one could find a relation between these two ideas. That's the goal of this talk. And then at the end, I'll come to the realization of these ideas in SYK. It's sort of natural. But are there any questions before I?
Yeah, can I?
Yeah.
Just in the general case, maybe it's an extra, but
Yes.
is the price not just the size of A, it's generally bigger, or how should I?
Versus the size, the price is generally bigger.
The price is generally bigger than the just size of the code subspace, or why is it not just the size of the code subspace itself?
Well, sorry, maybe I need to introduce what size is. Size is not the
I meant just the dimension of the
the dimension of the code subspace.
Sorry, not the size of the
because it's really about the I see your question. No. So in general, a code might scramble the information. So I think what you're asking is whether I could reconstruct, say, if I have one qubit in the bulk, I could reconstruct it from one qubit on the boundary. But in general, in a general code, I'm going to scramble one qubit's worth of information into many, many qubits. Very well scrambled code. I'm going to need potentially quite a large number of qubits on the boundary just to get that.
I think you have some sense of locality in the boundary where your A's are made out of some qubits. It's not just some arbitrary dimensional qubits.
Sorry. I understand. Yes, that's a very important point that I didn't bring up. Yes, when I'm writing this here, I've picked some tensor product structure for my boundary Hilbert space, which I will have to do also in this notion of size. So I'm imagining that, let's say, yes, Juan said the Hamiltonian on the boundary is local with respect to some tensor product structure. I could, of course, do some very non-local redefinition of my degrees of freedom, and then you're right. Then it would just be the same dimension as the thing. But yes, I have some notion of locality. Yes, sorry, thank you. Yeah, that's an important point today. Okay. Let me just mention how you might compute something like this. Well, the way we computed it, or one way you could compute it. So computing the price. So yeah, in our case, we're going to have the beta, this reference state, is the thermal field double state. So it's defined on two systems, or two copies of the same system. You have the left and then the right. And the question we're going to ask is, let's say I act an operator. I want to find the smallest region little r such that I can still reconstruct the operator. So little r is a subset of big R. And the notation we use is that the complement of little r is L union K. So this is K. Okay, so that's the one quantity which senses whether an operator is reconstructible from one region or the other is the relative entropy. So I can compute something called the relative entropy between two density matrices. I'm not going to tell you what this is, other than to tell you that when it's very positive, these two states are easily distinguishable on little r, and also for the other region, so the complement, so easily distinguishable. So the information is well, this isn't true what I'm about to say, but for the purposes of this talk, let me just say that when this is large and positive, that you can reconstruct the information or the difference between these two states on little r, and vice versa for L union K. And so a natural quantity to consider might be delta S, I'm going to call it delta S of K, which is the difference between sigma x acting on beta with respect to beta on R minus sigma x acting on beta with respect to beta on LK. Okay, when this quantity goes negative is when this is greater than this. And so it means that the action of this sigma x operator can be reconstructed on LK versus on little r. Sigma x here is just the poly bit flip on our code subspace that I defined up here. So it's just beta, beta, O phys plus the permission conjugate. Okay. And the reason we like to compute this quantity is just because it's a bit simpler to compute. It's actually the expectation value in this sigma x acting on beta state. So it's actually just equal to the expectation value of something called the generalized boost energy. Okay, where delta LK is rho LK tensor rho R inverse. There might be a minus sign here. I'm not. Okay, so and these density matrices here are for the thermal state. So I should say for beta. This is a beta expectation value. So this is like a generalized boost energy. When K is empty, this just becomes rho L tensor rho R inverse, rho big R inverse, and we know from the form of the thermal field double that that's just the boost energy. Or this becomes the boost energy. So it's some kind of generalized boost energy. And so what we're gonna say is that we want to find the quantity where this thing, where we want to find the K, let's call it K star, such that this is 0. So that's the K. So we fix sigma, and then we change K until this quantity transitions from being 0, from being positive to negative. So when it's 0, this thing is right on the edge of being reconstructed. And that will tell us about the price of the operator. Does that make sense? Really? Yeah. Okay, so that's the price. Now let me explain the operator size.
I'm actually confused.
Yeah.
You want delta S is supposed to be a difference of two relative entropies?
Yep.
I don't quite. I see. For the states beta and sigma x beta.
Yep. Yep.
Okay.
I haven't proven this to you rigorously, but there's a different quantity that's more rigorous that we can compute. It's just a bit more complicated.
Okay, but sigma x was projection operator on beta times O phys and what?
Sigma x is it's the bit flip on the it's in the code subspace, which was spanned by 0 in the computational basis, beta and O.
So you're just taking the, okay, so you could have just written no instead of sigma x.
Yes, I could have, yeah, yes, sorry. These are sigma x's, yeah, okay.
So I guess this delta is just the difference of the modular Hamiltonian.
Yeah, it's just the difference of the modular Hamiltonian. Sorry,
you could say that the difference in entropy is 0, and then
yes. This is not a rigorous quantity. What I'm doing, meaning it's not rigorous that when this thing goes to 0 is really when but it gets things right. But I don't want to go into the rigorous stuff. Okay. Are there any other questions? Okay, so I wanted to relate these ideas to operator size. So let me tell you what operator size is. So imagine you have a system of n spins. There are particularly simple operators, again, given some tensor product structure that's probably given to you by your Hamiltonian. where you divide your system into n spins, and then there are a bunch of these poly strings, which look like, you know, 1 on the first spin, tensor sigma x on the second spin, tensor sigma z on the 100th spin, and so on and so forth. So you have words built out of x, y, and z. And the size of a given poly string is just the number of sites not equal to the identity operator. Okay. So you can, for any system like this, you can double it and consider sort of the infinite temperature thermal field double, or which is really just the maximally entangled state. And then there's a complete, a nice basis where you act one of these poly strings on the maximally entangled state, and that's going to give you the state which we call P. And just for reference, if I want to get a state at finite temperature, I just do some thermal evolution on the maximally entangled state.
So this notion of size, that they don't have to be continuous or contiguous. You can have a bunch of poly matrices, then a whole bunch of ones, and then a whole bunch of poly.
Yeah. I don't have any. In the system, I think is the question about locality here, whether I should think of the in the system that I'm in SYK, which is what I'm thinking about mostly. There's no notion of, you know, this spin is closer to that spin. They're all coupled to each other, so I don't want to have to worry. But yeah, you could, I guess, in principle, in higher dimensions, or you had some locality, introduce some structure. So there's a size operator, which we're going to call V sub n, which, if you work it out, looks like the following. It's a two-sided operator. And where on each side I go to site I, and I sum this product where pi runs over sigma x, sigma y, sigma z, and the identity. And you can prove using just, it's pretty simple manipulations that I won't do here, that Vn acts on these states P as just, it multiplies by their size. So these P states are eigenstates of this Vn operator. There's another operator which will be important for us, which is called the K size operator, where instead of summing over every site, you just pick some subset. So you sum 1 over K, I equals 1 up to K of this same thing. Okay, and for a sufficiently, so what this does when it acts on these states P is it's the K size. So what that means is that it picks out the subset of K that you want, and it counts how many operators are in that subset. Okay. And for a sufficiently scrambled operator, we would guess that the number of basically, if I have an operator that really is sort of sufficiently scrambled, it doesn't really prefer one subset over the other. And so VK acting on that operator, acting on, let's say, beta, is going to approximately be equal to Vn acting on that operator acting on beta, basically because this is the ratio or the fraction of sites in the subset K, right? So roughly, if you zoom in on any subset, it should be representative of the density of operators should be representative of the whole. Does that make sense? This is sort of so this is for a scrambled operator, or relatively scrambled. So this means that you can get away, you can act with this K size operator so often and treat it as if you were acting with the full N size operator. There are these nice set of papers now. An important idea for us will be nice set of operators. Yeah. There's this idea of size winding. So I can take a general operator, and acting, let's say, on the thermoclear double, I can expand it in this complete set of states. Okay. And there was this special property that certain systems like SYK obeyed, which is that these guys, which are like the operator wave function, had a special property, which is that they had a phase which was linear in the size of the operator. So, and this alpha here is independent of the individual microscopic operator. It's just a constant. Okay. It will become clear why this is an interesting thing to consider in a moment. But what I'm going to argue for is that for size winding operators, there's a bound which relates alpha to the price. Okay. But let me just comment that we could have done all of this in SYK. So let me also just say that that the size of OR rho to the 1/2 is the sum over all the polys P RP squared, according to this ansatz, right? So what is alpha? So it's just some phase in this, but it turns out you can actually write a simple formula for it. So let's imagine we have some operator OR TR, which is just time evolved using the right-sided time evolution. What you can do is look at, so we're going to assume this operator is size winding. So this state has an expansion like this. You can take its time derivative. So you get Schrodinger's equation, which says that H OR TR beta. And then you can take this ansatz and you can differentiate it. Now here, when we time evolve O, alpha and RP both depend on time in principle, but that's it. Those are the two things that depend on time. And so what you find if you carry through the algebra, which I won't do here, but it's just 2 lines basically, that this is equal to the derivative, time derivative of alpha times the size. There was a term that came from differentiating RP, but actually when you take these expectation values, that term is a total derivative of the norm of O, and it's time independent, so it drops out. So what we find is that alpha is simply related to the energy, which is a constant in time, divided by the size. And you can solve that equation. So often size will be exponentially growing. Let's say in a maximally chaotic system, it grows exponentially in time. And so alpha is really just up to some constant. It's like beta times the energy of the state divided by the size. Okay, good. So what we found is that in this exponentially growing regime, these size winding operators have this phase which is related to the energy divided by the size. So you can actually write it out. Okay, but now to get back to the price, I need to talk about how this is related to reconstruction. So to do that, I need to tell you about reconstruction by teleportation. So there's a way of doing reconstruction using these size operators, which was discussed in this in these quantum gravity in the lab papers. There's reconstruction by teleportation. So you can imagine you have the thermal field double, and I'm drawing its bulk dual because it's easy to visualize. You insert some operator, let's say OR TR, and there's some operator on the other side of the thermal field double, which is sort of its CPT conjugate, which I'm going to call OL of minus TR. And if this guy is size winding, so meaning OR TR acting on beta, has this nice form, then it's not hard to see that excuse me, OL of minus TR is also size winding, but with the opposite phase. So it's e to the minus I alpha p RP. So what that means is that if I wanted to turn this operator, the action of this operator, into a left operator or vice versa, all I need to do is flip this phase. But there's a simple operator which does that, which is this size operator, which I erased. So if I act with e to the IG Vn, then I can, by tuning, by tuning G, I can turn this into an operator on the right. Okay, so I've effectively reconstructed this operator. Well, not quite, but I can use this to reconstruct this operator on the left, where here G, I need to tune to be alpha, to be 2 alpha, I guess. 2 alpha times that. Okay. If you do that, well, there's a bound, which means, so as I said earlier, if these operators are sufficiently scrambled, I could have done this using the VK operator because it acts the same way on these states. But then that means given some subset K, I can move this operator from the left to the right, or I can reconstruct the action of the right. So all I needed was K operators on the right, union the whole left, because I need to be able to use this operator, and I can reconstruct this operator on the right. So I could reconstruct it onto L union K. Does that make sense, people? So there's a bound which says that, so we need 3 conditions for this to work. So we need that VK is approximately V end. But that I just said is that the operator is sufficiently scrambled. And then we also need this bound, that beta is e to the IG is a pure phase. We need this condition. And then if I can make G equal to 2 alpha n, so VK is equal to K times P over N. So what I need is that G P over N, E times K is equal to alpha, or G or K needs to be alpha N over the size, roughly. Sorry, excuse me. Sorry. Is N alpha over G. Okay. But the reason I need this condition, let me just explain that, is because this is not a reconstruction, strictly speaking, of OR, because I haven't conjugated OL. So if OR is unitary, this operator is not unitary. But if I can conjugate this guy and only pick up a phase, then I can make this a unitary operator purely on the left, and then it's reconstructing a unitary operator purely on the right. And that's a true reconstruction of the right operator. And so what we find is that in order for this to be true, well, in large N systems like SYK, G can't be too big for this to be true. If I make G really big, then I get back reaction. The way to see that is just to compute the expectation value of this guy of this unitary in the beta state and demand that it be a pure phase. And the only way to do that is if G is not too large. A way of thinking about that is if G is really big, when I turn on this size operator, I'll throw in a huge amount of energy in the bulk and it'll back react. So using that bound, what I get is that this needs to be bigger than or equal to n, and alpha we knew was the energy, and over the size. So what we get is that k needs to be bigger than or equal to n times the energy of the original operator divided by its size. So in order to do this reconstruction, I need at least this many operators, okay? But notice that as time goes on, S is growing exponentially, so this is exponentially decaying. So I need fewer and fewer operators to get to do this reconstruction by teleportation protocol. Okay, so this I'm going to call K0. It's an important quantity. Okay. So this is the bound that we proved that really you need to do teleportation. You need a number of spins or fermions that is related to the size. Let's see, by this. And now I'm gonna tell you about SYK finally. Okay, are there any questions? Sorry, I may have gone through this a little quickly.
Do you assume this size winding behavior, how generic is that?
Good question. I suspect not generic, but I'm not an expert. I don't know if Henry has a comment on that, if he's here. I think the ability to do, so size winding is related to the ability to do reconstruction by teleportation. And I suspect that that's a fairly special thing.
Seems to be somewhat related to the SL2 symmetry.
Yes, it's related to the emergence.
SYK is related to global energy.
Yeah. But I think, well, Henry, I don't know if you can comment on this. I think at submaximal chaos, they still had something like size winding, maybe where alpha was complex. Yeah, okay, anyway. So it's not a purely, I don't think it's a purely maximal chaos phenomenon, but I'm not sure.
Can you hear me? Hello?
I can hear you.
Oh, okay. Yeah, I would say that it's pretty non-generic, but yeah, somehow at large Q and finite temperature, we still found something like perfect size winding, but yeah.
But alpha was complex.
Yeah, alpha was slightly, yeah, it wasn't exactly perfect size winding, but it was better than you would expect, I think, generically. So yeah, alpha has an imaginary part at finite temperature, I think.
Thanks. Okay, let me talk about SYK briefly, and then I can say, yeah. So in the context of SYK, what Ben and I did was we considered OR to just be time evolution of a single fermion. We also included some Euclidean time smearing. That won't be that important. But so as I said earlier, what I want to compute is the difference of these modular Hamiltonians, modular energies. So I wanted to compute this minus and dial K until this quantity became 0. So we know that whatever K that happens at needs to be less than or equal to this K0. Because certainly by this K0, because of size winding, because we believe that to be true in SYK, you should be able to do this protocol. And so you can reconstruct it to L union K from big R. And what we found is that actually this is parametric, that bound is parametrically saturated. So the K star, the K when this transitions is basically equal to that K0. And so the K, so I wanted to find, we want to find when this is 0, and what we find is that in SYK, K star is basically K0. So what this says is that quantum teleportation or reconstruction by quantum teleportation is the most efficient way of doing reconstruction, at least at large bit.
Is it related to the idea that the relative entropy of the thing you want to teleport is connected to the number of qubits that you need to be involved in the interaction or exchange with interaction?
Yes, well, let me say what I'm about to say about these dense matrices, and then maybe it'll. So how do we compute this? You can actually do this via a replica trick. So you have ORLK. It's actually a double replica trick in the following sense, or you have to analytically continue in 2 parameters. So you analytically continue n goes to 1. So here, n minus 1 is less than or equal to p. And the 2 limits you take are n goes to 1 and p goes to 0, but you differentiate about p equals 0. And that will reproduce. You could have done this in by doing 2 terms separately, but we wanted actually more information. So we did this double analytic continuation. And what you find is that actually this is related to, so you can do this, I should say, you can set this up in terms of the path integral and then solve these at large n using the G sigma equations, or there's another way, which is using twist operators. So let me explain this. So this quantity is, so here's the thermal circle in SYK. Because we have 2 systems, R and K, little r and big K, I'm going to divide the thermal circle up into two thermal circles that are coupled to each other along. They're coupled by the time evolution. But this is the K circle and this is the little r circle. Okay. And the whole left here is L. And this quantity can be computed by inserting a twist operator here, sigma NL, and a twist operator just on K, sigma minus N K. Okay, and then you have your state creation operators, which live over here. This is OR, this is OR. Okay. So this is how you compute this in terms of twist operators, but in the limit where K is much less than N, but much bigger than 1, you can actually do something like an OP or an expansion of this. You can just expand sigma minus NK in terms of a complete set of operators, expand in terms of all the fermions on K. And it turns out that this has the form of 1 plus sum K equals 1 up to K, little k equals 1 up to big K, size of K, sum over the replicas, I not equal to J, psi K, pi, psi K, J. Okay, times some OP coefficients here. And then there are other terms with higher fermion numbers. So this thing has an expansion in terms of the identity plus a 2 fermion operator, 4 fermion operator, so on and so forth. Has to be even fermion number. But now these I and J's here are the replica indices, and you can actually just find what theseCij's are in certain limits. Not too hard to do. And then you can plug this in basically to this correlator, and what you find after doing the analytic continuation is that this free energy, this generalized modular energy is just equal to, in the leading order in K over N expansion, that OR log delta L OR is equal to, delta K, OR log delta L plus, or really plus, integral ds f of s psi left of s psi right of 0 with a sum here. The sum goes from 1 up to okay plus other terms. So this is the leading sorry, this is all in. As an operator. And there are this dot 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 here has higher fermion number operators plus terms which will be subleading in this K over N expansion. And also there are terms in here, I should say, in SYK, this coefficient here depends on beta J, and there will be terms which are suppressed in beta J to the 2 over Q. So what I'm trying to point out with this is that in the large Q limit, this formula is actually interestingly not true. In the sense that if you take Q to infinity, but keep beta J fixed, there will be extra terms, higher fermion number terms that become important. But if you take beta J to infinity first, you get this simple relationship to this bilocal operator. And in SYK, this size operator that I mentioned earlier, Vn, takes the form of 1 over 2n, sum I equals 1 up to n of 1 plus I psi left psi right. And you can see just by inspection that, well, the K size operator is the same thing, but with K's instead of N's. You can see that this thing would be close to the K size operator up to maybe order 1 constants if this f of s were sharply peaked about s equals 0, and indeed it is. And to a good approximation, you can replace this with something like the size operator. So what you end up getting is that the expectation value in this state is equal to the total energy minus K times the size. Did I get this right? Yes. Minus K over N times the size. And so what you find is that for this to be 0, you need that K star is equal to N times the energy over the size, which is this K naught that I was mentioned earlier. So SYK approximately saturates, parametrically at least saturates this inequality. There are some order 1 coefficients here that are not exactly correct, but they're order 1. Okay. So that's the idea. Are there any questions?
Can I ask again about the relative entropy? Or maybe
Yes, no.
So teleportation, there's the idea that we have the relative entropy of the thing that we want to teleport. That tells you how many qubits need to be involved in teleportation. So how much information you understand.
Here by the relative entropy of the thing you want to teleport, you mean?
So suppose there is this override.
Yeah.
Create some excitation with somewhere in the bulk.
Yeah.
To calculate the relative entropy between this state and the vacuum.
Yes.
I think it's related to what you computed.
Yes.
And then that quantity tells you how many qubits you need to, or how many bits of information you need to transfer.
You need to transfer. Yes. Okay. That's a good point. I hadn't thought about. It's probably related.
But I think didn't you write a paper before saying that you could that this bound was actually sharp?
We didn't mention. You're talking. I know what relative entropy you're talking about, and I don't think we mentioned that, but it's a good point.
Not in this paper, but in some previous. Well, maybe.
Yeah. No. I know. I don't think
because we had conjectured that in our paper, but with the cons.
Yeah, with the cons co-cycle.
Maybe you prove something else. Maybe
I think we maybe proved something else, but it's worth looking at. Sorry. Yeah.
Maybe that's what you proved here.
I think maybe here it's likely this is more directly related to that.
Okay.
But,
so
but the size doesn't show up in your bound at all. So that's what I'm interested in.
Well, in some sense it does. The teleportation involves an operator which is the product of fermions on both sides.
Yes.
And that's the same. Essentially, that's the thing that measures the size. It would be a size in the sense of striker G.
Yes.
It's around the particular.
Oh, okay. So maybe we just redirect your bound. Okay. So.
But we didn't derive anything. We just conjecture. I think maybe you've proven it.
Oh, okay. possibly.
I understand correctly, because you're saying that the number of qubits you need is the relative entropy.
Yeah, it's related to the relative. Yes. Well, I think the relative entropy you said is just this energy, isn't it? Basically. You insert a unitary on the right.
I think we had the relative entropy was just the modular Hamiltonian of just one.
Yes.
wedge.
Yes. Yes.
So, okay,
Yes.
yeah, that's
I think maybe you want to subtract the thermal energy off. It's the difference between the state with the excitation and the state without. There's a order n constant that you just want to get rid of.
And the relative entropy for some small excitation is small, right?
Yes, yes, yes. That's what I mean. It's not the energy on the right. It's the energy on the right minus the energy on the left. Which I think
Well, it's somehow like the free energy on the right.
yes.
But the difference in free energy between when you added the perturbation.
Yes, 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 yes.
But you don't have exactly that, because you have this delta LK. You don't quite have the. Your modular Hamiltonians are not the modular Hamiltonians of the original wedges there.
But this energy is the modular Hamiltonian of the original.
Okay.
I suspect it's the same down there. But okay, we can talk about it. Okay, how much time do I have? 10 minutes. Is that right? Yeah. Okay, I just wanted to mention the bulk interpretation of the SYK result. And so this form of the modular Hamiltonian that I just erased, where we had log rho LK is log rho L plus this roughly size operator. Okay. This is reminiscent of what you would have. So the size operator, as we've learned, is related to the momentum operator, which generates null translations in the bulk. And so this looks roughly what we found is that this looks like this delta operator, this generalized boost operator, obeys an algebra that looks like delta x. This, what I'm writing, doesn't actually follow from what I've written here, but you can prove it. Or actually, okay, you can prove this in SYK. And you can actually, so in other words, you can compute this quantity and compute its expectation values in SYK using this replica trick. And what you find is an answer that looks like these two things are equal to this with some number here. So there's a number. And this is the algebra that would be obeyed if the following happened in the bulk. If there was a quantum extremal surface associated to the algebra L union K that came out to some point, let's say delta X quantum out here. And so you can view this calculation as a prediction for the position of this quantum extremal surface. Now, there aren't, we're used to thinking of quantum extremal surfaces as being associated to spatial subregions. in ADS-CFT, but here there's no spatial subregion in SYK. But so you might ask, what is the boundary region really? And it's really just K flavors of the fermion on the boundary. And you might, well, the answer that we get, delta X quantum at large beta J looks like K times beta times delta over 2 pi phi r 1 over beta J to the 2 delta, where phi r here is related to the boundary n over the coupling times this Kortzian coupling factor here. And the part that's interesting is this. This looks like, this matches, at least parametrically, the picture where there's a little region off near the boundary whose distance from the boundary in, say, Poincare coordinates is order 1 over beta J. And you're computing the change in the quantum extremal surface due to including this small region. There will be some entanglement that you pick out between the bulk fields here and the region here. And that bulk entanglement will scale like 1 over beta J to the 2 delta, where delta is the dimension of the boundary fermions. And so this answer parametrically looks like this is the picture. And you can check, well, yeah, so you can derive this from SYK, and it seems to agree with just a naive bulk picture. This is a bit funny because it's like you're taking some subset of the degrees of freedom in the bulk, partitioning them off, and then asking about a quantum extremal surface for that subset.
Would you interpret this 1 over beta J fact? I mean, this is the same factor that appears in the correlator, right?
Yep. Yep.
That's
Yep. Yep. It's just. Yep.
That instead of somehow having the K ferm, so you selected K fermions.
Yep.
But the amount of entanglement that this K fermions has with the other side,
yep,
is not K, it's whatever.
It's K over.
It's K over this beta
yes.
J, because that's the small correlation.
Yep, that's exactly right. Yeah. Yeah, basically in this limit where the what you want to compute is the mutual information between this small region and this large region. And in this limit where this region is very far off towards the boundary, the leading contribution to the mutual information is just the correlator of the lightest fields in the bulk. Those are the things that sort of the correlations that decay the slowest. And those things are controlled by 1 over beta J to the 2 delta. But it was important here that I didn't take a limit where delta went to 0. So this bulk picture, interestingly, seems to break down at very large Q.
Beta J somehow, log of beta J is the distance between the horizon and the boundary. If you wanted it to interpret it in a different way, like saying that that's
I don't think
say
so.
again what your interpretation was about the short.
So
segment.
if you include this region here, so that, sorry, the prescription that we're doing is we're fixing a region off near the boundary of some size. It has maybe some size scaling with 1 over beta J. And then we want to compute the quantum extremal surface associated to that subregion.
So when you say that size, that's size in what units? Or?
Yeah. In let's say in Poincare coordinates.
So this is size. Is that the proper length of this interval?
No, it is not the proper length. So yeah. Sorry, that's what's a bit confusing. But sorry, maybe the proper length of this guy goes like log of beta J.
Ah, okay, fine.
Yes.
Okay, all right, that's what you were saying. Okay, fine. Yeah.
Yes. Yeah, this is really like e to the minus. This is like e to the minus m times the.
Yeah.
That's on. Okay.
That length. So,
Go ahead.
Somehow, I thought that the log of beta J is somehow the distance between the horizon and the boundary. Somehow,
yes.
Don't have more space to.
Yes. I mean, it is. I'm working in a limit here where this distance is small. So effectively, the distance between this point and this point is the distance between. Yeah, this is all in a large. Yeah. So one interesting thing is so this delta here scales like 1 over Q. So if you did a limit where delta went to 0, so Q goes to infinity faster than you take beta J to infinity, you actually, this bulk picture breaks down. Sort of because you just have, I mean, sorry, I shouldn't say the bulk picture breaks down, our calculation breaks down. It might be that the bulk picture is still correct, but it becomes much more complicated because you have many, many light fields. Now you can take products of fermions and they're just still light. And so they are important for the entanglement entropy. So you need to include all of those. It's not just a simple 2-point function or p-fermion. So yeah, it would be interesting to do calculations in the large Q limits at fixed beta J, especially because at fixed beta J, well, yeah, it would be nice to understand how finite beta J effects correct this picture. But unfortunately, the only place where we have control over finite beta J analytically is at large Q, and then you have this technical issue of many light fields. But okay, that's all I had to say. Yeah. So.
Let me make sure I understand. So the formula you wrote there is not supposed to be valid for very large Q.
Correct. Yeah. No. I'm not sure. It could be still correct. I just can't do the I can't do this calculation.
Okay, so you don't know.
And yeah, we don't. I suspect it might still be correct. It's just that the entanglement entropy becomes, it's much harder to compute this number.
I mean, maybe this is obvious to everyone, but this difference that appears there, that's the same as the difference that Hong Lu, for example.
Yes. Yeah, I was gonna maybe say something about that, but I didn't. Yeah, so the fact that we found this algebra in SYK, there was this nice paper by Liu and Leuthauser recently where they leveraged at large n, they leveraged the fact that there were modular operators on the boundary that you associated some algebras on the boundary that obeyed a relation like this. And they argued that such a relation can only be possible at large n, because it implies that the algebras involved are type 3.1. And so here it's cool to see, I mean, it's cool to see a type 3.1 algebra. I mean, so here what we've learned by their arguments is that the large n algebras associated to these two regions need to be type 3.1. And so it's cool to see a type 3.1 algebra emerge from a system of qubits. I don't have much more to say. They wanted to use this operator to move inside the horizon, and it would be nice to try and do something like that. I think the calculations unfortunately get quite technical. Yeah, but
I guess the comment
maybe you had something else.
So because we have the symmetries of ADS somehow, we have that these modular Hamiltonians of the two wedges.
Yes.
So when you shift the one relative to the other, has this simple geometric action. So P plus, I mean, you can always define the P plus, but it has a simple geometric action.
Yes. Yeah. At least in this limit of small k over n, I think, well, yeah, that's where we can do calculations analytically. I'm not sure if, well, it'd be nice to know what happens. So, yeah, but yeah, it's a very simple relationship. That is a large n phenomenon.
Okay, if there are no more questions, thank you.